All right, so we're being recorded. All right, and I'm going to share the screen. As you all know, it's the moment of truth here. I'm down in Austin at my brother's place, if you haven't heard that. So I'm not sure about the internet, although he's got probably better internet than I do. And that's a note to myself and for you to turn up the cameras. All right, so here we are, episode 1. And we'll try and hit some of these topics today in our show. I passed by this today, and I thought, okay, here is a bookcase store. This person makes bookcases in Austin, Texas. He's on Guadalupe Street, and he's still in business. Maybe it's a she, but that was inspirational to me, because if this person can sell bookcases, nobody who has books these days. That this guy makes bookcases. I'm assuming it's a guy. I might be wrong. But I thought, if that person can do that, then certainly I should be able to do what I'm doing and survive. All right. So topics for tonight. I'm going to have Max go get the original Mr. Askew, if he's in a mood. My brother, So my nephew Max I was telling them, he just graduated from Texas A&M in electrical engineering, but he is here hanging out with my brother here in Austin, so he's around. But I just asked him to go get the original Mr. Askey and let you meet him. He taught in Norman from 1975 to 1978. He taught biology at West Mid High, which is now Alcott Middle School. But people still are upset when they find out that I am not, this is a little bio on him, I am not the actual Mr. Askey. I'm the second version. But in 3 years, he became legendary for his biology teaching, his strange way of teaching biology. He ended up teaching in Austin at the college there, and he retired a few years ago. But he's hanging out up here. So, well, let's keep going. If he gets him to come in, then we'll say hello. All right. So, already said this. Join the Facebook group, Askey's Physics Show. Join the group me. You don't have to join the group me, but it'd be better to communicate that way. I'm not sure how you do that. I may have to have your phone number or something, but I don't do a lot of group me stuff. I do it, but I don't really run them. And then make sure you subscribe to the YouTube channel. I will eventually have our own YouTube channel, and I'll put our stuff on there. But for right now, I'm just going to use my YouTube channel that I had. Okay, so here we go. It's just a camera here. So here's the this is the original Mr. Askey. See the resemblance? About 10 years difference.
Yeah, my wife told me I should dye my hair to be the same as David's.
Yeah, see, of course, I don't dye my hair. I don't care what they say.
No, nor do I.
Yeah.
I don't know how you'd guess.
So anyway, so you were at West Mid High for 3 years, 75 to 78, and then you've been in Austin ever since.
Starting 70, 74, 75.
So it's 3 years,
75,
right?
76. Yeah.
I think you said 75 to 78. 3 years, though.
Yeah, right.
Taught with Ed Merrick, and if you know much about education in Norman, Ed Merrick's a pretty big name.
Yeah. He went on to be a professor at OU, and he was head of our science department. We had a lot of fun. I could tell some crazy stories, but I don't know if I should.
That's why. It's the family show.
You can't even do that stuff anymore.
Yeah, right. You couldn't get away with it. They used to have all kinds of snowball fights and everything.
Oh gosh, we had a water fight you wouldn't believe. The halls had about 3 inches of water. We were throwing buckets of water at each other before it was all over. Yeah. Anyway, we had a lot of fun.
Anyway, so
maybe one of y'all's parents might.
They probably do. Just ask them if they had Jay Askey.
Back in the day.
Yeah.
So, well, Nice seeing y'all.
All right,
I hope
there he is.
you'll enjoy my brother's
Yeah.
class.
Now you know. He's the. I've said some things about you, so that's. All good. All good.
Yeah, okay. Yeah, just keep it there. Thank you.
Yeah. All right. So anyway, so join the YouTube channel if you haven't yet. And okay, so yesterday I went to the I should have I don't know why I didn't. I had it on a small screen. That was stupid. Anyway, yesterday I went to the UT and looked for the physics, and they have a physics, math, astronomy building. Wasn't that impressed with the outside of the building, but and then because of COVID, most everything is closed down. This is one of the engineering buildings there. I was just surprised how large. I mean, compared to OU, how big is UTU at twice the size OU, something like that.
Area or students?
Students, about 50,000 or something, or more.
A&M's bigger than.
Oh, really?
And I think UT one is downside, so I think they're in like the 40s or something.
Oh, really? Wow.
I'll let
Okay.
you know in a second.
Yeah. Well, they're still quite a bit bigger than OU. In fact, just walking to look at the chemistry building, there was a biology chemistry building, and then I looked on the left side, another chemistry building. It's like that is this place is huge. As we walked around, Jamie and I walked around campus. They have all kinds of cool statues and stuff. This is all canoes and boats. I thought that was pretty awesome. Um, we're good on light. I have my own lighting if I need it. I think we're good.
40,000 undergrads as of.
That's smaller than I thought it was. This is what's left of your bike. Now, what is this? What is this person here? Huh? You lock your front bike. You expect somebody's not going to take your bike? Anyway, it looks like it's kind of a rough campus on leaving your bike at places. This is where the physics building is. You can look down. There's the famous tower. And then the physics building here is pretty nondescript. I did notice this. This is as you walk in the door. Student honor code. We supposedly have an honor code at the high school, but they're much more serious about it in the university. So as a student at the University of Texas at Austin, I shall abide by the core values of the university and uphold academic integrity. But I know even at OU, if they catch you once, that's one thing. You catch you twice, then you're kicked out of school. So I imagine it's about the same at Texas. All right, and then as I was walking, I was wanting to go to the library to see if I can talk to some people about research that's going on. The library was closed, but I did find this. This is interesting. This takes it from 9 a.m. to 3 p.m. This is just an example of some of the research you guys can do. This was actually done a couple of years ago, but it's a big poster up there. And what do you think this is? Any guesses as to what this is? What this represents, this graph? Take a look at it there. Hey, Max, you can even join us on the Zoom if you want. Have you seen that yet? Anybody have any idea what that means? It caught my attention. So what this is they've taken audio of an older person's home, and this is a person who's starting to suffer from dementia. And so anytime you see brown, it means the TV was on. And anytime you see these colors, it means they were talking to somebody. And so to see all that brown there in the afternoon, part of their soap operas, right? Their stories came on. But they're trying to make a link between this and dementia and like the importance of interactions. And so I guess they did, and all they did was they took an audio and then they put in the different frequencies, you know, for human voice versus television and all that, and just measured it. And I guess they're making some kind of correlation. But I thought that's kind of the cool stuff you'll do as research. I don't know if that was undergrad or there's some information about it. I'll put a link. I'll put that picture on the screenshots with some descriptions on it. There's another one on chaos. This is actually electronics in chaos and a well. Now that's not a real well. That's just a computerized well. But they ran these simulations looking at chaos theory. And in the first simulation on the left, there's no restrictions. You notice it spends more time in the well. It spends more time in the well. Let's go this way. There you go. Spends more time in the well here, and it's random when it's randomized. This is randomized, except that there's a rule that you can't go in the well. So I guess it kind of seems to make sense. And then this one, you can go anywhere you want, but you can't leave your path. And so it just kind of shows. I thought, well, probably some application to physics and the bending of space, time, and light, and this thing thinks it's going in a straight line. And then there's, let's see, here's something on UT and telescopes. It's all closed down now because of COVID, but I know that leads us to this one that I wanted to show. For a physics major at UT, it lists all these physics courses, which means nothing to you. It doesn't mean nothing to me either, because this has a bunch of numbers. But if you come here, it'll talk about them more. This is for astronomy, because I know Jacob's interested in astronomy, and it lays out your 4 years, your fall and your spring. Is that what A&M does too for
Yeah, you
engineering?
can find them online if
Yeah.
you Google.
Yeah, and these guys, I'm sure Brandon has some of these people that are already getting ready to go that route. But here you go. So here's some of the courses you need for astronomy. You do need mechanics. Now the physics mechanics, they call it Physics 301 here. That's the physics that I teach. All right, and I'm sure it has calculus with it. And then electricity and magnetism, that's the next course you'd take. We used to teach that in Norman High called Physics 3. Wave motion and optics. Okay, it's all about, we do our simple harmonic motion, all those waves, a whole course in wave options, wave motion and optics, and then modern physics laboratory. Now, this is not for a physics major. You also take an astrophysics course, stellar astronomy, galaxies, and then all these other intro, planetary systems. It looks like a pretty cool curriculum. Of course, you have to, if you take these kind of courses, you don't just take physics, you don't just take astronomy, you have to take all these core courses, and a typical course is 3 hours. So like it has English, humanities, American history, you got to take 2 sections of that. Mathematics, they're already in your major, so they didn't show those. And then here's some of the physics that you do take. I think this is for one of the physics majors. Modern physics and thermal. Remember we talked about thermodynamics. The number one rule, we talked about the 3 laws of thermo. We talked a lot about entropy and the second law of thermo. And thermodynamics is one of the hardest courses, just because it's the study of heat flow, and it's really the formulas. I mean, I guess it's somewhat intuitive, but I know it was hard for me. That's a killer course for engineering students. And then we get into this physics laboratory. Those are always cool. Classical dynamics. So remember we talked about there's a difference between statics. We do statics problems where nothing's moving, all forces must equal 0. And then we do a lot of dynamics problems. And that's why we spend the first part of the year studying kinematics. We study kinematics the entire first semester, because in college, they're going to blow past that in 2 or 3 weeks. And you get left behind right off the bat if you don't really understand derivatives and, the difference between acceleration and velocity. Then you get to electrodynamics, quantum physics. This is foundations, thermo, quantum physics 3, quantum physics 2. And finally, there's also biophysics here. I don't think OU offers biophysics. So if you're looking and biophysics it's like those of you who want to go to med school, I mean, biophysics is a great major to take. And finally, this is from Zach Burkett. I just got this yesterday. I'll read this to you. He said, I'm finishing and he was a student in my class, and he struggled. I mean, he was a great kid, but he struggled mightily in physics, especially on the tests. And he said, after finishing my first semester at OU studying civil engineering, I had a 1.56 grade point average. And that ain't good. No, I wasn't a dumbass up for debate, but I was just a bad student. I came very close to dropping out and opting for something easier. He said, I'm proud to say that 8 years later, I just passed my PE exam. Now, when you guys become an engineer, you have to you go ahead and get your degree. That's great. And then you got to study for a couple of years, and it costs a couple $1,000. You have to take your professional exam and in your field. And that will be the hardest test you've ever taken, because once you pass it, you're a professional. I mean, then you can start to hang your shingle on and go out there and start making some real money. But he finally passed it 8 years later. Once he got through his freshman year, he celebrated 5 years of working with Oklahoma Department of Transportation. He said, don't let the past failures dictate your future. I thought that was a pretty good thing to say to you guys, that if you're having struggles, that's the thing about engineering. You don't have to be a genius or even physics. You just have to be a hard worker. Just keep working at it. What you're doing right now, getting the terminology, getting all the. Okay, and then I happened upon these four guys when I was up there yesterday, and I'm going to change my sound, and I'm going to play this for you. It's a 2-minute little clip. I'm going to play this. All right. I got to change my sound so it's not my AirPod anymore. Okay, let's see if this works. Okay, tell me if you can, give me thumbs up if you can hear this, but here we go. Wait. All right. Physics questions. These are not physics questions. Okay, so I'm interviewing. If you mind, just tell me your name and where you're from and what you major.
Sure. My name is John Fong. I'm from Malaysia and I'm majoring in geotechnical engineering, which is a subset of civil engineering.
Okay. Now, so let me explain this. So I was going around the engineering buildings at UT, and I wanted to get talk to the professor, and I was just kind of impromptu went over there. Thought maybe I'd catch some students, and man, there was nobody. Because it's intersession right now. I mean, it's not even intersession. There's just nothing going on campus. Half the doors were locked. But these four guys were out there flexing, because they just graduated. So I thought that was pretty cool. And I stopped and asked them, and they said, "Yeah, we'll talk to you for a minute." All right.
Hi, I'm Pratik Bhope. I'm from India, and I graduated with a master's in electrical and computer engineering this
Okay.
spring 2021.
Thank you. So he's electrical and computer engineering, master's.
This is Mrunmay. My major is geotechnical engineering, and I'm from India.
Thank you. He said geotechnical, I think, engineering. And this guy just graduated too.
I'm from India. My name is Arjit Sarkar. I recently graduated. My major is technical engineering, and yeah, it's great to be here.
I'm going to ask you one question each, okay? What would you suggest if these are bright high school students, they're looking to go to Texas or wherever they're going to go? See, I had to make it sound good, right? I couldn't say they're going to go to Oklahoma. They might have booed me out of there. So who knows? Maybe you end up going to Texas. And major engineering or physics or something, what's some suggestion you'd give them? As far as words of advice.
Words of advice. It's not all about the math and sciences. Teamwork is the most important thing, fostering relationships. And never underestimate yourself. I think you can do a lot more better. You can do a lot better than you think you can.
I love that. I think that's great because I know a lot of students are lone rangers in high school, and you can get away with that, especially with COVID, right? I mean, you didn't really talk to anybody hardly. You cannot make it. I'm telling you, you will not make it past your freshman year of college if you're sitting in the library studying on your own. You've got to form groups. So and there's a lot of people think of nerds as engineers, but you've got to have buddies there, to work with you, to share the load.
Well, I would just say, just reach out to people when you need help. Don't give up, irrespective of the circumstances, and always have the end goal in sight when you're working on the written things.
Thank you.
Yeah. Maybe try to see physics everywhere around you, like you see examples of classical mechanics all around you. So yeah, try to relate what you said.
Yeah. I like that because that's what Natalie was saying to me. She said now she's had my class when she drops her pencil or when she's driving her car, she's starting to think of the relationship or the formula or the graph. And that's what you kind of get. You get in that mindset. All right, then let's go to the last guy.
More about the education, what you want to learn. At UT, you get a whole package. Basically, starting with your own personality to your physics, you could see things happening around you. Application, theory, everything together. So, yes, cheers. You should come to Texas.
I love this. All right, you come to Texas. All right. Well, there's a little. Now, I'm sure Max could give a Texas A&M one, but.
I was about to say, come to Texas A&M. Don't go to UT.
Ooh, Texas. UT. Well, okay. So we can't be saying too loud here. All right. So you guys still hear me now? We're ready to move on. Okay. Get off that. Okay. So, yeah, I thought you guys ought to see those gentlemen. All right. So we're going to do a little bit now. Now there'll be in the show. I'm always going to try and do an interview or do a video or some little clip besides just sitting there working physics problems, for an hour. But we are going to do a little bit now on gravity, and because I know we've already talked about gravity some, but there's some interesting points to gravity here that I want to get into for a little bit, and then we'll start to wrap things up. Any questions so far? You guys can turn your audio on, or you can do it on the chat. So far, so good. All right, open that up. Okay, so we talked about Newton's law of universal gravitation. That was 1687, which is amazing. He did it from basically data from Kepler's. It went way back to Kepler, but data that they had collected for years. Kepler didn't understand it. He did it in the late 1500s. He thought he was trying to honor God, right? But he collected a lot of data, and Newton, Galileo, some others looked at it. Well, from that data, Galileo figured out the inverse square law. Did not know, so blow this up. Yeah, he did not know what G was. They found that out, and I have that here. They found that out at the Cavendish Experiment, 1798. So exactly 111 years later, they finally figured out. We've talked about this in class too. I have that little thing hanging from the ceiling. But they figured out what G was. I think each one of these, this is a class mock-up, but this is the actual Cavendish experiment. I think each one of those were like 400-pound lead balls, and they had them separated. It was in a near vacuum, but that was the experiment of the time. And from looking at that torsion wire and how much those, in this case, the red smaller masses went towards the gray masses, how much it bent a little bit. That was from there they determined now he's a laser. They determined from the angle of reflection and then understanding how much torsion that wire can handle, they figured out the force or what G was, as we see here to the that's only 2 siggies, but they go like 5 or 6 siggies on the G. And what I mean by siggies, Carson, is how accurate the number is, like how many decimal places. So that's universal law. We've talked about that. We've done a problem or two on that. And it is an inverse square law, which that's an inverse square law. And then can anybody remember what the other inverse square law we talked about was? If you can chat it or you can say it. We just mentioned it a few times. It's electromagnetism. But we talked about the relationship between gravity when we were trying to figure out what gravity was. Yes, Coulomb's law. Thanks, Nick. So Coulomb's law is also an inverse square law. Instead of having masses on top, Coulomb's law has charges on top. Then it has the Coulomb's constant. Instead of having G, instead of a gravitational constant, there's Coulomb's constant. And Max can tell you all about that because that's all, statics, which then leads to, did you guys ever study Ben Franklin? Because
No,
Ben
we didn't
Franklin's
quite
the one
get
he's
to the lightning and the key thing.
yeah. The story on Ben Franklin is that him and his buddies used to go drink beer, and they go out in the forest, and they would hang this child from a tree. Now, wait a minute. They would hang him, but they would hang him. The kid loved it. He wasn't hanging by the neck. They would strap cord around him and hang him so he's horizontal, hanging from the tree. And then they would somehow, I don't know what they used to get him all static charged. Then they would put a bed of feathers down, and all those feathers would come flying up, and the kid would just look like a chicken, They just thought that was hilarious. So that's what that was
Seems
the
like
extent.
something you do when you're really drunk in
When
the
you're
1700s.
drunk, sitting out, you brew your own beer, and Franklin was a partier. So that's a funny story though. But then they, electricity, Orsted, and all those guys. We're looking at 1800s. Of course, Faraday. We talked about Faraday some. We watched a film on him with induction and first motor and all that stuff. But yeah, Coulomb's law actually was about the same time as it was 1700s, whereas Newton probably in that same vicinity. So it's a lot like Coulomb's law is a lot like. It's just weird that gravity and electricity seem to be fundamentally they're both inverse square. So in this graph, it shows that the idea of an inverse square. And if you have a 1 Newton apple, if an apple about 1 Newton, that's about a quarter pound. So you have an apple about a quarter pound at the surface of the earth. That's 1 Newton. And if you go out, it's inverse square, right? So the apple then when you go out twice as far, and that shows D, it's a little bit confusing. D is not in diameter, it's in radius, the radius of the Earth. If you go out another radius of the Earth, that apple has now 1/4 the weight. It's still the same mass, but it's 1/4 the weight. If you go another radius away from the Earth, now it's what do you say it's going to be? You can put it in the chat or you can say it. Because now look, the masses are the same. The mass of the apple, the mass of the earth, you get 1/8 almost the mass of the apple, mass of the earth. And the G, of course, doesn't change. That's a constant. So how will that apple's weight change when you're now 2 radii away from the center of the earth? You're getting out, now you're 6, 7, 12,000 kilometers out there, 13,000 kilometers above the earth. So you're up there where the I think geosynchronous are up in that range, way out there. You're not, the moon is way out there, but I mean you're up there pretty high. So at that point, the apple weighs 1/9, right? It'd be 1/9, and then if you go 4 times or 4 times the radius, you're out there at 1/16, and then 1/25. So the apple's weight drops off, never to zero. Notice that does not go to zero, okay? But it just keeps getting closer and closer. So you eventually you even the moon obviously is being held by our Earth's gravity, but you lose your weight, just drops off, not your mass, but your weight drops off. And then there's this one. I've already kind of worked it for you, but it's we didn't get to this year. It says determine the G on the International Space Station, and just using the formula. And so because I'm not going to make you get out your calculators right now, but if you do the math on that, this is looking at the Earth versus the mass of the ISS, and then you divide it by the distance between the center of the Earth and the ISS, and you're going to get unstable internet connection. It's not good. You're going to get you guys still see me okay? You're going to get a G of, instead of 9.81, it's 8.8. So those astronauts in the ISS, this might be news to a couple of you. I don't think if you're in my class, I hope it's not news to you. But maybe Carson hadn't heard that. But if you're out, they call it 0G, right? Because those astronauts are floating around. So the question is, if their G is about 10%, it's only 10% less than our G here on Earth, how can they float? Why do they float around? Why do they, you see them up there? And anybody want to give either a verbal explanation or try and type something up? Why do you think they float? We've mentioned this before, and my hint is elevators. This is one of the last things we talked about was Einstein's happiest thought in I think it was 08 or 09. Why would the ISS astronauts float if they have about the same gravity we have? Hopefully you're typing. Max knows.
I have a guess.
Oh, here we go. All right, so Jacob says the astronauts and the ISS are accelerating at the same rate. They're both falling back to Earth. So relative to the ISS, the astronauts seem to float. And I couldn't answer it better. So it's like being in an elevator. I sent them to the tallest building in Oklahoma City, and they didn't cut the cable, but they were looking at their weight, how it changed with the elevator equation. So if you cut the cable on an elevator, you would float. You'd feel like you're floating for a little bit until you hit the ground. So they're essentially free falling. I heard this in college, and I remember walking back to my dorms, and I was a knucklehead, and I thought, man, that ISS, or wasn't ISS, it was Skylab back then. I said, that Skylab sure is a hot way up there to fall back to Earth for years and years. I wasn't the sharpest tool in the shed, but Hey, we all make those mistakes. And why? Okay, that's my last question. Then we'll get off this. Why then? Humor me. Why then would it not hit the Earth if, like Jacob said, it's in free fall? Why don't they hit the Earth? We talked about this before, but briefly. Somebody joined us, I think, or they left. Why didn't it hit the Earth? Maybe that's maybe Sasha. Oh, say Sasha, how you doing? Sasha's here. That's good.
Pretty
Sasha,
good,
we're
thank
just
you.
talking. Hey, doing well. We're just talking about the ISS and astronauts falling back to Earth. So, anybody with Jacob, I think Jacob's got it, but does anybody else got an idea why those astronauts, if they're in free fall and they're floating around in the ISS, why don't they finally hit the Earth? You think they would? We explained the floating, but we never explained why they don't hit the Earth. See, I think that was my problem. Is my professor threw it in there at the end of class and then kind of left. Maybe that's why I became a physics major. Okay, so Nick says it's probably orbital speed. And do you guys know what the orbital speed is? I've mentioned this number a few times. Nick says inertia and circular motion. The ISS is orbiting around the Earth because it's resisting the Earth's gravity. It is, well, I mean, its inertia is resisting Earth's gravity, but you're right. The key is the orbiting around the Earth. And now the question is how fast does it have to orbit the Earth so that, here's the Earth, here it is. It wants to go tangential, right? It would like to go tangential to the Earth, but Earth's gravity keeps pulling it back, or Einstein would say the curvature of space-time. But so it thinks it's going straight. It wants to go straight, but it's really going this way. So as it orbits, right? If it orbits if it goes too fast, it'll eventually kind of start to go out to a higher orbit, which is really hard to do. It takes a lot of energy. But if it goes at just the right speed, then it will, circle the Earth. And it's never a circle. It's always somewhat elliptical. There's always some eccentricity there. It's a terrible drawing, but it goes in a little bit of an ellipse. And what we need to do is, since I can't give points for this, we ought to have some kind of point system. So, and then at the end, you would get a big prize. Free 4-year scholarship.
Am I delayed for that?
I don't got any money. We get you something nice. Whoever
You trick
wins.
him into thinking you're gonna pay for it.
Yeah, so I'm going to give Nick and Jacob a point. And Io, he didn't answer a question yet. So, who can ever answer this question? Hey, and I'm okay with you looking it up. It's legal. I'm not going to sit there and try and stop you. How fast does the ISS go? Somebody look it up real quick and then type it. We talked about it, but it's one of those numbers that when you teach it long enough, you just remember it. Yeah, that's it. Close enough. I think it's 17,500 is the classic number. 17,500 miles per hour. That's miles per hour. Max wouldn't do that. He'd go kilometers per hour. Oh, so Io just said for about 4.7. That puts it in perspective. Miles a second. I mean, who do you think thought of that number? I mean, that's it's true. That is the number you have to orbit. And who was it, like Neil Armstrong or somebody, or Einstein? Who the heck would have? I mean, who would have figured that number out? How fast we have to go to orbit the Earth? What was that scientist? Oh, yeah, Jacob's correct. It is Newton. So Newton obviously did not orbit the Earth, but Newton said, if I could put myself on a mountain high enough and I put my cannon and shoot that cannon, uh, the speed at which that cannonball goes around the Earth and comes back and hits me in the butt, that would have to be 17,500 miles an hour. Once he determined the law of universal law of gravitation. Okay, so still used today, and I don't want to get into this. We're down to 7:07, and we still got some time though. This one I'm not going to work, but when you're doing this is a classic kind of gravitational problem you'll have. We didn't do this one this year, but it says the question is they give you the masses. So A is 400 grams, B is 100 grams, C is 50 grams. and you're supposed to figure out how much gravity is on B, comes from A, and comes from C. And so you have to put it all together and do like a gravity profile. And so I say it's a stack and rack, right? This is a stack and rack area because we're going to have to go I roofs and J roofs. You guys call it I roofs and J roofs at Texas A&M?
For
Thick.
the different vectors, or
Yeah, for the unit vectors. Like we called them, I called
So
them.
we did IJK at community college, but now I is current and J is the
Oh,
imaginary
right,
number.
right.
So,
Yeah, you don't want to do that now.
X hat, Y hat, Z hat.
Okay, so you call them hats. My professor called them, I tell them I caret. I never liked that.
Hat if it's a triangle, tilde if it's a wave.
Yeah. But Walter Lewin, who I go by, he calls them I roof. He has that Lithuanian I roof. So we say I roof and J roof and K roof. Anyways, this is an I roof, J roof problem, and I'll tell you what I'll do. This is in the ASCII's physics show Facebook group, this problem. And if you want to just kind of stimulate your brain a little bit, work this one, and then I will include a key to it, how to work it. But that'll be your funsies practice problem. Just what you want to do in the summertime. Talked about that. Okay, now I want to talk a little bit about gravity anomalies. This is the cover. I still want to start a group. There is the Flat Earth Society. I want to start the Deformed Earth Society, and I think I could get a lot of money from. There's enough morons out there. The Earth is deformed. If you look at this is a high relief. I mean, it's not this. This is gravity anomalies. Where you see it red, that's where you weigh more. Where you see it blue is where you weigh less. So where gravity, using that Newton's universal law of gravitation, I'm not saying you weigh more. Like in Europe, in Germany, up there where Max is from, he would weigh more if he came on a Caribbean cruise. And over here is the okay, so there's the Western Hemisphere. If he went on a Caribbean cruise, he'd lose weight. Now he's not going to lose 10 pounds. I'm talking an ounce. I mean, not much, but he's being pulled with less. There's less mass below him there. So you can see like the Andes Mountains, things like that, where there's a lot of mass below. Yes, you are further away from the center, but there's more mass. There's a lot more mass, and I'm talking dense mass. Like granite is looking at six times water, so you get some pretty dense rocks, and you're going to end up weighing a little more. And in fact, why I'm bringing this up is not because of that. It's because of this. This is it's a gravimeter, and this is a $50,000 gravimeter. When I did my degree in geophysics, and my senior Max did a thing on his lawnmower. My thing was to do a gravity survey of the Rockies, of a section of the Rocky Mountains. And in fact, that data got used in some of this, apparently, because they've got this big database. But I used this guy right here. That's more of a that's not a $50,000. That was like $5,000. And I sat and still like this guy. I went for 3 weeks all around the mountains, and we grid out a system, and then I would do a gravity survey and that. But then this one, what this guy has in the field, and what this is a much nicer version. So Dr. Alan Whitton, who is this guy right here, he was the first one to do, like we do rocketry, we do all this kind of stuff, robotics, right? He's the first one. In 1998, he came to me and said, I want to do something with geophysics with your kids. And so we would do an 8-week seminar every year, and then it turned to a 12-week seminar. But he unfortunately had a heart attack on his bike. He was in much better shape than me and died. I just found out a while ago that his son, who was my student, that's his son. He's now a professor of geophysics. So I got to go look him up. This is the book that Alan Whitton wrote as Geophysics and Archaeology. He has dinosaur bones named after him. He scuba dives off the coast of Madagascar looking for things. He wanted me to go to Jordan with him one summer because they were looking for pharaoh tombs, and I couldn't do it because I had little kids. But anyway, cool guy. So here's why I bring it up. He has this machine in my room. I told you this before. Remember I said that you put this in one's tile on the east side of my room, if you're familiar with my room. And then on that one, on the east side, the value of G, and this went all the way out to 1, 2, 3, 4, 5, 6, 7 ciggies. That's why it's $50,000. The value of G on that side of the room, on the east side, um, yeah, on the east side, by the door, when you come in the door, it's 9.823467. That's what we said G was there. And then if you go to the west side of the room, kind of by where the gray fridge is, it's 9.823295, and it was consistent. This is extremely accurate. You could put somebody, you could do the G at the floor, do it on the floor. It takes about 5 minutes, 5 to 10 minutes for it to level, and then you got to wait, can't move, and then you can put it on the table, and it would actually be less because it's further away from the center of the earth. So this can find things. We did not know why that was. We thought there was some kind of cave underneath, or there was a tunnel or something, and it turned out the reason was. Anybody remember why? Tell me why you think. If you remember why, we had this in conversation once in class. I don't know if my virtual kids did. Yeah. So Matt said it's because there was a steel beam on the east side, on the west side of the room. If you look up right where we did it, there's a steel beam, and steel's got a density of 7. So it's 7 times what water is. So steel's really dense. So I was being pulled up to that beam. And so that's why this determined that there's a difference. So why I'm bringing him up is because of this. It's because what's in the here by the way, here's what you would do if you're looking for gravity anomalies. And as I was doing my Colorado thing, I would do it like every 30 feet. I do another one, or 50 feet, whatever it was, and then I'm looking for the gravity, and I do this all these one-dimensional. But then you do a grid system, and then you can put them together, and I'll show you the grid system. But if there's, say, heavy rock underneath you, say there's an intrusion, and it's not too far. Well, it doesn't matter how far down it is. It could be 2 miles down. That's the cool thing about it. Then you're going to get a gravity anomaly. Anomalies, of course, in a place that's not normal. And so all of a sudden you see a bump, and you say, hey, there's something buried under there. There's something down there. Either it's something denser than everything else. And so you think if you can start mapping it out, you can find out where the fault starts, where it ends, and where you might want to drill if you're, if you're a petroleum engineer. And then the other thing is, though, what's used mostly are for caves or for areas of low density. Dr. Whitton and his crew looked for weapons of mass destruction in Iraq. He was one of the crews that was out there looking for Saddam's underground, because they're looking for anomalies like this, areas where there's a cave or something underneath. And so you end up doing 3-dimensional, and if you do a grid system above, you get a 3-dimensional view like that, and you can start to say, whoa, there is some kind of, and this is by the way, it's a very cheap way of doing it. I mean, you're going to have for me, it was a $5,000-$10,000 instrument, and then I was a student, so I got paid nothing. I paid them, so they take my data, and then instead of drilling holes or doing logs, they do well logs are expensive. Geophysics, seismic is expensive. You can do a very cheap, quick run with gravity. So why is this important today? Because of what happened last weekend, the Tulsa race riots, right? This has been all the news. And so in 2000, I think it was 99 or 2000, before I had never heard of the race riots because they don't teach it in history. Some people had known about it, but they were from Tulsa, but this was, I'm sure you're familiar with it now, but 300 people were killed, massacred. They were burning down. It was called Greenwood District. It was Black Wall Street in Tulsa. It was one of the most affluent black neighborhoods in the world, or in America certainly. And there was the whole thing where a guy supposedly had raped this white girl, but it really didn't. I don't know the whole story. I don't remember the whole story now, but anyway, so the big mob came and were going to lynch them, and then they settled them all down. Then the next morning they blew a whistle and they all just attacked all these white folk. They were even dropping dynamite from airplanes onto buildings, onto houses, and onto structures, and they burned that whole part of town. Right? Okay. So you guys have heard the story. Here's the article that came out of there. There's a bunch of articles. But this is one of the first articles out of it from Dr. Whitton. And so what we did is we went to Tulsa. I went along with him. It wasn't my idea. I was going with him. And me and then students, also my geophysics student. One of those girls is now a geophysicist. But we went to Tulsa and we set out a grid system at a cemetery where they thought there might be mass graves, because like something like 300 people were killed. Were they buried them like that night? They didn't have the decency to give them a funeral, so they burned them alive and then buried them, and then supposedly they hauled a bunch away in cattle cars. It was just horrific. But with a gravity survey, we did a gravity survey on that cemetery, and with this gravity survey, you can tell whether the ground, of course, it's a cemetery, right? So yeah, there are plots, but you can tell there were no graves in this one area, and so the legend was that's where the mass graves were. So we went with geophysics, and we started off with gravity survey. We did a grid system, and we did a gravity survey of this area, and sure enough, we found what looked to be like there was something down there that wasn't just normal soil. Down, I'm talking about 20 feet down or up to 20 feet. There was some other formation. It's probably more like 6 feet. But then that was enough to bring in what's called ground penetrating radar, and that's ground penetrating radar. And so the New York Times was there, and the Boston Club. There's a bunch of people there. National Geographic was even there. But I didn't do this part, but they did this ground penetrating radar, and then they could see, and this is not from Tulsa. I couldn't find the one there, but they could tell that there's a lot of this is below the earth. This is a profile view of the earth, and I don't know how far down it goes. Those are two-way travel times, so it's not feet. It's in geophysics, you talk about time, how far below it is, because how long it takes the wave to go down and come back up. It's two-way travel time. So, half a second tells you the depth. Anyway, this is showing that below the surface, there was all this upheaval. So somebody had buried something there and then left it. And sure enough, they started digging. And this is, I'm not sure if this is the Tulsa one, but this is where they're doing. So I think this is the same place we were. That's the graveyard. They found a lot of bones and stuff. So they had buried a lot of people there. So that's a rather gruesome, but I went in and talked about it because it's in the news right now. A view of using geophysics, using gravity, and then later using what's called ground penetrating radar. Okay. I'll tell you what, let's get to this. I want to talk about Dr. Strauss, and we'll get into this. This also takes us a little bit to string theory. So there's no way I got 10 minutes. I want to see if you think you can get, so I'm going to start setting up. I'm going to go mobile here in a second, and we'll end up with trying to see if we can see what Max has on his autonomous. He was in, okay, so Max was in a group. Sometimes group work doesn't work out really well because if you're the hardest worker there, you end up doing the job. And so I was just telling him, don't be a lone ranger. But sometimes there's always that one guy or two guys, three guys that don't do jack, and then they show up when the cameras are on, though. By golly. Okay, hold on a minute. That's just, what are you gonna do? All right, so I'm gonna go mobile here and share. This is the last thing we'll do. I'm gonna do a new share. How do I do this? I'll stop the sharing. Okay. And now I have multiple people sharing. Let me see if I can get myself to share here. This is new for me. Oh, join with video. Okay. Okay. This meeting's being recorded. Okay. Continue. And I don't want to mess up the audio. Here we go. Okay. Now, spotlight for everyone. Make the host. Okay, now I'll make this the host. Okay. Now, can you hear me? I'm going to take this. Let's see. Hold. Let me take that off. Okay. That off. Can you guys hear me okay?
Yeah.
Okay, now I'm going to get away from the, still haven't made me the host yet. Hold on. Make. Let's go to this. Oh. Okay. Oh, okay. And I'm going to turn this on. Right at that. Now. Okay. Now. Oh. Okay, now it's just me. No. Now, can you see me? This is.
It's still echoing pretty bad for some reason.
Off the sound. Okay, now I muted that. Now hold on a minute. Okay, I'm making this the host, and okay. Turn that off. Turn on this sound. Audio, sound and haptics. Silent mode, no. Silent mode off. I knew this was going to be my main problem. I knew this was. I had a problem. It's going to be it. Let me try now. Turn speakers. But okay. All right. Let's change it. Turn it off. We're going to try something else. Okay, we're going to try something else. I'm going to kill that. I'm just going to kill that. I'm just going to kill my phone. Getting off. Leave the meeting. In. No. Leave. Just going to leave. Okay. Sign. Okay. Now I'm back, right? We're good? You hear me? I'm going to take that off. Undo that. You guys can hear me. Good. Okay. And now we're going to go. Follow me. The whole phone thing was a good idea, but it does not work. This is Jay, my brother's abode. Going out to the front to end this thing. Okay. Around the shed playing chess. It's kind of weird. Okay. Kitchen. Coming around to the front where the lawnmower is. An example of a project. Okay. That phone didn't work. I'm going to go with this. Just go with the laptop.
Fair enough. Excuse the mess in the back of my truck.
Okay, so here is the prototype. You guys see that all right? Give me a thumbs up. You guys can see that. Maybe.
Yeah, that's a little more on target.
Thumbs up. Can they hear me at all? You guys hear me at all? Okay, hold on. They're still here. They haven't left. So, okay. Sophia's saying the lag is real. Really bad lag. Okay. So it's bad lag, but let's take a look. So just really go ahead and talk. It'll eventually happen.
Yeah, so it's been somewhat disconstructed because of things I had to give back to the department, and it was a little bit of it wasn't too great because group projects can be pretty lame when you have a 4-person group with 2 people that basically didn't do anything, like 0 contribution at all. So, my ramblings aside, we built an autonomous lawnmower that almost kind of worked a little bit. It turns out that's a lot harder to do than you think. So we got 2 controllers. I actually made this, like, designed this circuit board and had to print it and soldered all this on there, everything on there. I don't know if you can see, but this chip is like smaller than a quarter and has 144 pins. So you can imagine how much fun I had with that. I'm not trying to say I'm really good at soldering. I was just really frustrated and tried for a really long time.
Okay.
And then this is more of a commercial, like off-the-shelf controller that was way easier to use. So hindsight 2020, use the hobby option, they're way easier. But yeah, so this technically there's a GPS that goes here. It reads GPS and it would read all these sensors and then report back to the controller right here where we have an obstacle and GPS location. And then from here we got 2 motors on the back wheels, and I don't know if you can kind of see it, but the front wheel, it's called a mecanum wheel, but it can essentially like roll perpendicular to the axis of rotation. So that allows us to kind of stop and do a 0-point turn. And we had some issues with that because some sensors failed and we weren't actually able to tell how much we really turned. So that was our biggest issue. But yeah, then we got 2 electric scooter motors, kind of like those bird scooters or whatever you call them that drive around. We got 2 of those, and I'd be willing to bet this thing probably goes about 20 miles an hour if you give it full throttle. And a little blade here, which honestly, I'm surprised they let us put a blade on this because I was kind of worried someone would lose a finger or toe, but nobody did. Power supply up in this beautifully purpose-built HEB brand Tupperware. And that's how it worked.
And so it passed the test.
It passed the test. It went in a rectangle. Like I said, we had a really hard time turning corners because we had like 3 sensors fail at the end, and like I wrote 2 semesters worth of code in the last 2 weeks because the person that was supposed to didn't do that.
Didn't show.
If it sounds like I'm bitter and upset about it, it's because I am. But we graduated. Some of us more deserve it so than others.
Okay, so I'll keep going here. I'm going to wrap this thing up. But Max, he says he's bitter, and he is, but he's going to get a master's now and got with a good professor. And a lot of that in a master's is what professor you get with. And so he's got himself a good one. So he's going to stay at A&M and get his master's in electrical engineering. And then when he comes out of that, he'll probably be making around $90,000 a year with a master's in electrical engineering. Depends on what his field, what part he goes into. Okay, so that was a little haphazard. That's why this is June. See, June is me experimenting. I'm finding out what doesn't work. And I'm pretty laggy, I guess. So I dropped the whole phone idea. That's not going to work. This phone is laggy unless you plug it in. Okay, so we're back and we're out of time. I'm going to go ahead and wrap things up here. Now, before we go, okay, are you guys, can you hear me again? Are we good? Thumbs up? Somebody give me a thumbs up. Okay, good. Now, before we go, I want to show you where we're going here. And sorry, it's taking a little longer than I thought. Okay, so we're gonna get into this next time. We'll get into some of these crazy equations. We're not going to be able to understand them all, but we'll go.
What you consider a crazy equation?
That's the different kind of forces. There's a E and M anyway, but that's some crazy stuff. Maybe Max can help me out with that later on. The weak nuclear
I know some
force.
of those symbols.
I know. So we know some of the symbols anyway. And then, we'll get into like what Dr. Strauss, when he comes to class, and he couldn't come this year, and he's agreed to come next year. Maybe I can get him to come this summer and do a little bit. I don't know if he's in Switzerland or not, but he'll talk about standard model. He goes to Large Hadron Collider. This is our class the last time he was there. And then he'll stop and talk. He's talking to Tony there and Brennan, but he's a good guy. So we'll talk about some of the stuff he's found, and it has to, believe it or not, it has to do with gravity and forces. So we'll get into that a little bit next time. This also will also spill into string theory a little bit, and some work by a woman named Lisa Randall. She's one of the world's experts in string theory. And I already introduced Max. Okay, so on episode 2, then we're going to do that. I'm going to show you some good physics sites to go to for catching up, or just for getting for maybe Max has some for me too. But there's the Walter Lewin that I started off going to. I think Doc Physics is one of the best there is. And I'll put all this next time in the notes. And we'll also get a little more on pulleys. We'll talk more about, some of the pulley systems, which you didn't quite get to this year either. And we'll show how they all relate to work and energy. And we'll get more formal with work and energy next time. Okay, so I'll be back in my studio at home, and so better, or not necessarily better, but more reliable internet, and I won't try and go mobile on you. Okay, stop that. So thank you all. We're running over. I'm going to stop recording. I'll pause the recording.